Ah, but it don't get much dumber. It don't get much dumber than trying to forget a girl when you love her, and I still need you.
In the previous component, we looked at this idea of Q, the reaction quotient, and how it is a Mach equilibrium constant. It has the exact same form of the equilibrium constant, and is used to test the relationship. When Q is equal to K, that means the system is at equilibrium. When Q is larger than K, that means that the system sort of is too heavily loaded with the products, so the system would have to run backwards to reattain equilibrium. And if the equilibrium constant was larger than Q, that would mean that the reactants were in dominance, and the system would have to drive itself respectively one way or the other to obtain the correct formula. So in this case, the reaction would be driven from products towards reactants, and in the other case it would be driven from reactants towards products. And we can use this to gauge which direction a reaction would proceed. Now that's a qualitative aspect. Up to this point, we've used concentrations to tell us equilibrium constants. Now what we're going to do is we're going to use equilibrium constants to predict concentrations or partial pressures at equilibrium given a set of starting conditions. So let's take a quick look at an example. You have at 1000 C, 12,000 C, the equilibrium constant for the following reaction. Br2 gas is in equilibrium with atomic bromine, Br2, and the equilibrium constant has a value of 1.1 times 10 to the minus third. If the initial concentrations are 0.063 molar bromine and the atomic bromine is 0.12 molar, what would be the concentration of these species at equilibrium? Now, again, there's some key language here, some key language that we're looking at. They say the initial concentrations, that they don't tell us what the concentrations are at equilibrium. We have no knowledge of the equilibrium concentrations. So this is a hallmark of a problem where we have to use equilibrium constant information. So again, one of the first things we do is we start with the balanced chemical reaction. Br2 is in equilibrium with 2Br, and those are both gases, and the equilibrium constant for that is equal to 1.1 times 10 to the minus third. Additionally, from our knowledge of what an equilibrium constant is, we can generate a form of this equilibrium constant related to the concentrations, where it's Br squared, all divided by Br2, raised to its respective power, which in this case is 1. So these two bits of information together, we can relate to concentrations. And they tell us that at the start, the concentration of Br is equal to, and we'll just call this initial, is equal to 0.012 molar, and the concentration of the Br2 initial is equal to 0.063 molar. In last week's lecture, we had brought into this idea of the algebraic relationship between stoichiometric quantities. We know that at equilibrium, regardless of where we start, the starting concentration of the bromine minus whatever is consumed in the reaction, in this case X, would be related to the amount of atomic bromine initially plus whatever is changed, 2X. And so we can use this information and we can plug these values into our equilibrium constant, because we know that at equilibrium, again, these are the equilibrium values, we know that these values at equilibrium would be represented by these quantities. So let's just plug those in, and we get the following. 1.1 times 10 to the negative third is equal to the quantity for the bromine. In this case would be atomic bromine, Bri, plus 2x. But remember that this represents all of the atomic bromine, and now that is squared, all divided by the bromine, Br2 iodine, initial, minus x. What we have now is an equation that has one unknown, x, and that represents the change from initial to equilibrium. So all we have to do is do a little math to rearrange this equation and solve for x. So let's do a quick algebra review using this very specific example. Just rewriting the equilibrium constant information in the algebraic form, we can relate these values via x. And so if we plug in the actual concentrations that we were given in the problem, we see that from the initial concentration this becomes the following. 1.1 times 10 to the minus third is equal to 0.012 plus 2x squared, 0.063 minus x. And now we have one equation, one unknown, and we can rearrange and solve. Now, just a reminder, when we rearrange and solve this, one of the first things we can do is we can bring this over to this side of the equation. So let's do that. If you are an algebra god, you can skip until the next section. I'll try to put a little highlight in there. I'll put the time that you could skip to in the little notes, and you can skip through this. I'm going to work this out stepwise. 1.1 times 10 to the minus third times 0.063 minus x will equal 0.012 plus 2x squared. Notice I'm not simplifying, I'm not factoring or anything like that. I'm not multiplying things out, simply because we can do the bulk of our operations beforehand. Now, the next step is to multiply this value in. Just as a reminder, a times b plus cx would be equal to ab plus acx. Order of operations and algebraic rules where everything becomes multiplied. And so in this case, we would multiply things out. This would become, doing the math, multiplying these out, this would become 6.93 times 10 to the minus fifth minus 1.1 times 10 to the minus third x. The x doesn't go away, equals 0.012 plus 2x squared. Now, with most of these, the whole thing we're trying to do, the process that we're trying to get, is to move all of the x's to one side of the equation and to move all of the constants to the other. Though in reality what we're going to find is that's usually not how we do it, but that's the process that we're working towards. Now the next time, this is a square term. And these are coefficients, and so in this case a plus cx times b plus dx, we would do FOIL. First, inner, outer, last, and we would multiply our components respectively to obtain the correct values. And so working this out, 0.24x and 0.24x, that's where we do the initial multiplication of these. But there's two, we do it twice, so this becomes 0.0048x. I'm sorry. It only is. This would become 0. This would become 0.048x plus 4x squared. Now, once we are there, we start combining terms that are of the same exponent. This is x to the 0. This is x to the first. These start to get combined, and this is the x. This is the x squared. And so we start to combine those mathematically, additively, addition and subtraction, because they're just addition and subtraction at this point, to get the following form. And the way we usually solve for these is we try to arrange it, because what we're doing is, again, we're trying to move all the x's to one side, but because we have this square term, we end up with a problem. We can't just solve for x. We can't just take the square root. It doesn't work. All right, because if we take the square root, what we'll find is that we have a square root of x somewhere else. It doesn't work unless there's no. This is basically because it's a quadratic. So let's take a look. If we start adding things up, set everything equal to 0, equals, and then we rearrange, we move all these red ones onto the side, and then this green one moved on to this side. Mathematically, this becomes 7.47 times 10 to the negative 5th. This becomes 1.1 exponent negative 3 plus 0.048 plus 4.91 times 10 to the minus 2x and plus 4x squared. Now, the reason we do this is a quadratic. Now, there's no easy way to solve this except to use the quadratic equation. Quadratic equation is the following. Given a polynomial that has the form ax squared plus bx plus c, regardless of what they are, we can rearrange and solve for x using the following formula. X is equal to negative plus or minus square root of b squared minus 4ac divided by 2a. I always wanted to say that. Anyways, so once we have that, we can plug in and solve for x. Rearranging this equation into that form is one of the reasons we set that equal to 0, and so we can use that information. So once we have the quadratic form, and then we have our data arranged in that format, in this case 4x squared plus 4.91 times 10 to the minus 2x plus 7. 7.47 times 10 to the minus fifth is equal to 0. We are left with just math, where this would represent A, and this would represent B, and this would represent C, and we rearrange and plug these into the quadratic equation and solve, and that gives us two numbers. It gives us two values for x. One of them will make chemical sense, and one of them won't. You're not going to be asked to memorize the quadratic equation. You will be asked to use it. If I want you to use it on a test, I'll provide it for you. Or I may provide it for you and you won't use it, one of the two. But still, you should be able to use it. One of these values makes chemical sense and one of them doesn't. And how do we tell which is which? Well, we have to use our chemical knowledge, all right? So let's take a look at our starting assumptions. If we go back and we take a look at our starting assumptions, we see that, that the atomic bromine, Br, is equal to the initial value minus 2 times the change in x. 2 times the change. That will equal our concentration of bromine at equilibrium. Well, and then the other value is similar. But on paper, this is 0.012 molar plus 2x. Plus 2x. Well, if x is a negative value, if we were to then take a look at this one, if we were to plug this value in for 2x, this would say, well, it's gaining a negative, which really means it's losing. This would become 0.012 molar. Doing the math, doing the substitution, doing the multiplication, minus 0.0210. And so what this means with that at equilibrium, we would have negative, we'd have negative 9 times 10 to the minus third molar molecular iodine. Well, you can't have a negative molarity, all right? And so they say math is no good for anything, all right? But these numbers are real quantities. They represent something. So this would represent the condition that is untenable for our reaction. And so instead, the equilibrium value is x. X is equal to negative 1.78 times 10 to the minus third. All right. And here's everybody makes the mistake. Yay! X is equal to negative 1.78 times 10 to the minus third, and then they stop doing the problem. Right? What did the problem ask? It didn't ask you for x. It asked you for what the concentrations of each species at equilibrium. So we know that this is 0.012 molar plus 2x will be equal to bromine, atomic bromine concentration, and 0.063 minus x is equal to the molecular bromine concentration. And so if you plug in those values, you get 8.44 times 10 to the minus third molar for the molecular bromine, and 6.48 times 10 to the minus 2 molar for the molecular iodine. And now we're happy. But no, you aren't happy. If this is the correct answer, you should be able to take these values and plug them back into our equilibrium constant. K is equal to 8.44 4 times 10 to the minus third squared divided by 6.48 times 10 to the minus 2. And that should give you your equilibrium constant again. Plugging those back in, I get the following: 1.09 times 10 to the minus third as our equilibrium constant. Page back a few pages, you'll see that this is exactly what's given in the problem, 1.1 times 10 to the minus third. All right. So now we can be happy. Now we can really be happy. We've checked our answers. And then Dan holds this little sign up that says yay. All right. So, wow, that sucked. All right, that was miserable. That was really long, really horrible, and in reality, superfluous. We can brute force solve. That is true. But oftentimes, there are tricks. And so let's talk about the tricks in the next